So in section 6.2, we're on the second page. We're ready to talk about buffers. So we've had a lot of, excuse me, we've had a lot of little bits and pieces about buffers. A little bit came up in Unit 5, a little bit came up in 6.1, a little bit came up in the page before. So we already know that a buffer is a solution that contains two things, a weak acid and its conjugate base. So I'm going to write them like this. It has a weak acid and its conjugate base. The way that you would see it in AP terms or chemistry textbook terms, the weak acid, HA, and the conjugate base, A with a negative charge. So the A negative is the anion. So if you want the ideal buffer, and this is already written down for you, the best buffer is where the amount of acid and the amount of conjugate base are equal. And this happens at a specific point. We had it on the graph yesterday, here, the halfway point. The ideal is at the halfway point. And at that point, we also have this very important relationship where the pH at the halfway point is the pKa of the acid. And so we can learn a lot from the titration curve. This is one of those things. So for a buffer, pH equals pKa plus the log of anion over the acid. So remember this equation that we talked about earlier, and it's on your AP formula sheet. And this is how it looks on the sheet. It's very slow. So this is the buffer equation. If you want it by name, it's Henderson-Hasselbalch. So at the equivalence point, that should say halfway point. So at the halfway point, I don't think you have this part written down. At the halfway point, excuse me, this fraction of anion over acid, or conjugate base over the acid, equals 1. And in case any of you have forgot or never knew this, the log of 1 is 0. So at the halfway point, this whole part disappears and you end up with this in the equation. So that's the relationship we already know. So before you get there, so before the halfway, what do you have more of? The anion or the acid? You're starting with a lot of acid and it's being converted to anion. So before the halfway point, you're going to have more of this thing on the bottom, and so it's less than 1. It's going to be a fraction, something between 0 and 1. So how does the pH and the pKa compare? So what's the log of a fraction? So let's make up a fraction. Let's look at okay. So the log of something between 0 and 1 is a negative number. Because really what you're looking at with a log is this. You're looking at the value of the exponent. And so this is a fraction, it would have a negative exponent. So what you have is, this is going to be a negative number. So which one's bigger, the pH or the pKa? Let's look at it like this. This guy's got it written down all messed up. So I made up a number, I've got the log of 1/2. So it's minus something. Which one's bigger, the pH or the pKa? Very good. Once you get past the halfway point, a lot more of this weak acid has reacted away. And so you're going to have a lot more conjugate base. And so the top number is bigger, which means greater than 1. We got pH equals pKa plus something, because the log of a positive number is, or the log of a number greater than 1 is going to be positive. And so which one is bigger here? This is an awful lot of numbers and stuff to make sense of this. Just look at the graph. So let's say, you don't need to redraw this, but this is the general graph. So here's your equivalence point. And that means right here is your halfway point. It's exactly half of the volume. So here's my pKa. And if you just follow this along, before you get there, pH is less than the pKa. Because if you choose this point right here, here's the pH and here's the pKa. So you should be able to look at the graph and figure this out without having to plug it in this mess of an equation. That makes sense? If all else fails, I would always look at the graph. It's much better. And the same thing after. So you look at it here. If you draw the line over, here's the pH. It's greater than the pKa. You don't have to worry about figuring out, is the log of a fraction positive or negative? You don't have to worry about all that. So just look at the graph. It's going to save you a lot of trouble. Now we're talking about making buffers. So example 2, we want to create a buffer with a pH of 3.74. Wow. I don't know how much longer this board is going to last. 3.74, and we want to use formic acid, and its Ka value 1.8 times 10 to the minus 4. First question, explain why formic acid is a good choice to create this buffer. First off, it's a weak acid. So that makes it a good choice. So it's easy to make a solution in which you have its weak acid and its conjugate base, with HCOO minus. So it's going to be easy to make this type of a solution, which is a good buffer. Here's the other thing. You could have lots of different weak acids. It doesn't mean it's going to be a good buffer at a pH of 3.74. The best buffer in the best scenario wow. I just wanted to finish out the year. All right. So we want to have one where the pH equals the pKa. And so we need to see what is the pKa of this. And that'll give us an idea of how suitable it is as a buffer. So pKa is the negative log of Ka. pKa is 3.74. And that's exactly where we want it to be. And so this relationship is good. This is the best buffer when the pH equals the pKa. So if you want a buffer for a pH of 3.74, formic acid is a great choice. If you wanted a buffer at 3.74, acetic acid would probably not be a good choice because its pKa is about 4.74. And so it's way out of the range. If this is going to be the best, excuse me, the notes say this is an ideal substance to use since its pKa equals the desired pH. Let's write that down. This is like an AP answer version here. This is an ideal substance This is the kind of thing that AP likes to see. You explained everything, you did it in one sentence. A lot of you on the mock exam, there was a couple of questions in that last exam about acids and bases, especially on the very last question. Your answers were like 3 or 4 or 5 sentences long. And I had to read them, and they were long. And those graders feel the same way because they grade the same question 150,000 times over the course of a week. Keep it short and accurate. Examples 2b and 2c are going to illustrate 2 ways that you could create this ideal buffer. So we already said since this buffer is at the halfway point, pH equals pKa. Number of moles of formic acid equals number of moles of HCOO. So in part B, it says how many moles of solid sodium formate should be added to 100 milliliters of 0.1 molar formic acid to create this buffer. So we want to know how many moles of formic acid are here. And that's just volume times concentration. 100 milliliters is 0.1 liters. Concentration is 0.1 molar. 0.01 moles of your formic acid. Which means we have to add 0.0100 moles of sodium formate to create this solution. This is kind of your AP answer version again. And in case you're wondering, this sodium right here is going to be a spectator ion. We really don't care about it. We only care about that anion that it gives us, that conjugate base. The nice thing about sodium is that 100% of it dissociates, so we don't have to worry about it at all. It's just there because the charges have to be balanced, and that's it.
Why don't you have 0.01, 0.005? Pick up half of it. Why don't you want only half of it too?
Well, this is going to be half of it, because we've got 0.01 moles here and 0.01 here. Yeah, we don't want to think about it in terms of halves, really. We want it to be in terms of the moles of each one are equal.
But when you unequal, wouldn't that take to the equivalence point instead of halfway point?
The equivalence point would be where this and this were equal, because this is the actual reaction happening, and this would be the equivalence point. But when we're talking about the acid and its anion, again, I'll see if we can't get back to this right here. The acid and the anion are the same number.
Oh, I was thinking about adding a base.
Yes, you were. When you add the base and they're equal, you would be here. Yes. So the first way to create an ideal buffer is to combine equal moles of the weak acid and its conjugate base. Second method, in part C, we're adding a strong base. It says what volume of a 0.1 molar potassium hydroxide solution can be added to create this buffer. So this second way, we are going to titrate to the halfway point. Either way, method 1 or method 2, we're getting it to that point where moles of the weak acid are equal to the moles of conjugate base. So with this one, the first way you would do it is calculate to the equivalence point. So we have 100 milliliters and 1,000 milliliters, 0.1 moles of. So there's the acid. This gives us number of moles of the acid, volume times concentration. For every 1 mole of this weak acid, we need 1 mole of the hydroxide. Again, the potassium is a spectator, we can completely ignore potassium. And then the concentration of the hydroxide, 0.1 moles of hydroxide for every liter or 1,000 milliliters. And if you look, there's a lot of units that cancel. So there's milliliters of hydroxide, and there's a lot of numbers that cancel too. 0.1, 0.1, 1,000, 1,000. And so to get to the equivalence point, add 100 milliliters of your KOH. But there will be no acid left here. We want to titrate it to its halfway point. So equivalence point is 100 milliliters. We want to titrate it with 50 milliliters. So there were two methods. One, add the salt of the weak acid, sodium, whatever. Second option, add hydroxide to the halfway point. So those are the two ways to make a buffer. Either way, you're trying to get it to that same point right here. Whichever method, that's where you want to be. So at the halfway point, we're talking about the best buffer. This is where it's most effective. But the buffer zone goes beyond those limits. If you look back at your graph here, a buffer could potentially work anywhere in this range. And it's pretty much anywhere that this slope is more or less constant. Because you'll see over here there was too much of a curve. Over here there's too much of a curve. But in between them, any buffer here will work. Doing it right here allows it to shift farther either way. If you pick a buffer that's right here, you might have a problem where you go beyond this line, and that's called breaking the buffer. So part D, we want a buffer with a pH equal to 4.00. It's not too far off from 3.74, but it's not exactly 3.74. So it says how many moles of solid NaHCOH, so sodium formate, should be added to, and it's the same solution as before, 100 milliliters, 0.1 molar formic acid. So first off, the desired pH is greater than the pKa. So here's what we're expecting. And again, let me go back to that graph. The desired pH is greater than the pKa. So we're looking at having more conjugate base than we have acid. More conjugate base than weak acid. Because if the pH is higher, we've gone beyond the halfway point, which means more of the acid is gone. So here's your equation again. Just a note, they have the same volumes. So we can just stick moles in here. And this was in Unit 5, the very last question on that AP assignment that I gave you. It said something about this right here. And I told you that if this were the end of Unit 6, I would expect you to know how to do it. At the end of Unit 5, no. So this is the pH we want. This is the pH, or excuse me, the pKa, plus the log of, and what do we know? We know how many moles of formic acid we start with. And what we want to know is moles of the formate ion. So really this is, you could say this is X moles of formic acid. Formate, excuse me. Just can't talk to me. And you would solve for this. So, I don't know, this may be, I'll just go through it. So here's my 4, I'm going to subtract 3.74 to the other side. And so we've got the log of X over 0.01. To get rid of this log, most calculators, if you hit the second button and then the log button, you'll get that 10 to the X. So let's see, this is really 0.26. So 10 to the whatever, 10 to the 0.26. Yeah. Trying to do it in private, I'm going to mess it up. But that's basically how you would do it. And you should come up with 0.0182 moles of formate. So to get the buffer at that higher pH, you have to have more of that conjugate base. So here's the halfway point. We're probably right here. So the numbers kind of reflect that we have more of this conjugate base than we have the weak acid.
You just put in 0.01 moles. This isn't a different.
So what it's saying is that if the volumes are the same, if they're not, then it has to be a little different. So it specifies concentrations, but if they're in the same container, in the same solution, then their volumes would both be the same. So we're probably talking about adding a solid sodium formate to this. And so they're both in this 100 milliliter solution. And that's how you can get away with using moles instead of concentration. I think the bottom of that page for you is blank. There's a bunch of stuff written down. Brief summary. You have a buffer when a solution contains a weak acid and its conjugate base. A buffer resists a change in pH when a strong acid or strong base is added to it. When it's a buffer, you could use that Henderson-Hasselbalch equation. Ideal buffer at the halfway point, where pH equals pKa, acid concentration is equal to anion concentration. Two ways you can create a buffer: adding equal moles of its conjugate base through a second compound, or adding half of the moles of a strong base to get to that halfway point of the titration. All right, let's stop there.